So, as you see, I've written a couple of problems that you can work on if you like. I suggest to work in groups. It's easier to, it's nicer to discuss. So first of all, there are many problems. I don't know. I have 6 now, and of course, it will be quite impossible to solve all 6 in 1 hour and a half. So, but I put that many problems because you can choose what to do. So if you don't understand something and you would like to do something else, you can do whatever problem you want to do. Of course, always approach me. And if you cannot read and don't understand, then of course also ask me. I will just walk around throughout the session to see how it is going. So
you're taking an exam?
I'm taking an exam, yes.
Let me pick the best.
I will go briefly through all the problems, so we are on the same footing. And of course, if you want to have them as a copy as well, the problems, you can ask me and I can send them to you. So, first problem is about Turing machines. Yesterday we talked about the concept of Turing machines. And here we define a language for palindromes. So we have bit strings. The language consists of words that are made out of bits, such that if you read the bit string from back or from front, it's the same thing. So as an example, I will just erase it after 0110, right? If you read from right to left or left to right, it's the same. So that's a palindrome. And the question in this first problem is to sketch a Turing machine that decides this language. And here actually it's helpful to use 3 tapes. I just write in 3 tapes. This might help.
Can you read out the subscript of the...
Oh, yes. So this is xi. So x is x1, x2, up to the last. So xi equals x subscript the length of x plus 1 minus I.
Oh.
Yes.
Oh, that's
Yeah. So the second one is about complexity classes, classical complexity theory. So we define the complexity class co-NP, which consists of all languages that are where the complement is in NP. So a language is in this class. If you take the set of all words and subtract the language, then this one is in NP. So, and the thing you can prove here is that if NP is different from co-NP, then P is different from NP. Okay. So 3 is about quantum circuits. Throughout yesterday and today, we have seen some quantum gates. One of them is the Hadamard gate, which is defined like this. And then we have the controlled NOT gate. I hope you can read that. So if the first system is 0, then nothing is done on the second. But if the first system is 1, then the second is flipped. So a 0 goes to 1, a 1 goes to 0 on the second. And so I ask you here, what do these circuits implement? And here, this one, the middle one, is a controlled NOT, but just upside down. So you just change 1 and 2 in the expression, right? So this will be identity tensor 0, 0 plus this tensor 1, 1. Okay. So today we defined the class of decision problems efficiently solvable with the Deutsch version of the closed timeline curves. And we said the languages in that class, if there exists a Turing machine such that the Turing machine halts in time polynomial in the input size, and it outputs a circuit, a description of a quantum circuit, such that if x is in the language, then we will measure 1 on the first qubit with probability 2/3 or more. If it's not in the language, then we measure 1 on the first qubit at the output with probability 1/3 or less. And here are the measurement operator that we use. and this is the formula for calculating the evolution in this model. But at the end, this was very fast. Today in the morning, we talked about the post-selected closed time-like curves model, and here I ask you to write down the class of language decision problems that are efficiently decidable in that model. And this model works as follows. It's actually very simple. So you can see that the output is computed by C row C dagger, and then you have to normalize. So we divide by the trace of this, so such that this is a quantum state. Quantum states are normalized, where C is just a partial trace over the unitary, over the causality violating part. Is this clear? Like I said, if you have questions, please come interrupt me now or come to me later. All right. Fifth problem, a bit harder, is once you have defined this class, show that NP is contained in that class. And to do that, it is enough actually to show that SAT, so the language which consists of Boolean formulas that are satisfiable, to show that SAT is in that class. Right? Yesterday, I talked about saying that satisfiability problem is complete for NP. This means if you can solve a satisfiability problem efficiently, we can solve any other problem efficiently. So to show this inclusion relation, it's enough to show that SAT is in this. And this is rather a more difficult question, but if you like to do that, it would be nice. And finally, there's something I did not talk about, but this is kind of going more towards my research, what I did previously, actually. We kind of define a model which is inspired by closed time-like curves, and we call it a unique fixed points model. And we define a deterministic unique fixed point algorithm. And this algorithm is a polynomial time algorithm, like here, that runs in polynomial time of the input size. And the algorithm, if we give it x, it outputs us a Boolean circuit, so it is a classical circuit, such that the circuit has a unique fixed point. So here is the existency quantifier with an exclamation mark. This is a uniqueness quantifier. So for every x, this algorithm outputs a Cx such that there exists a unique y. If you put in y, we get y out. Okay? And now we can define a complexity class based on this model. And it consists of all languages where there such an algorithm exists, where if x is in the language, if and only if the fixed point, so this unique y is uniquely determined, the fixed point starts with a 1. So z is any bit string, we don't care, but the first bit is a 1. So if x is in the language, then this holds and vice versa. And then show that this class is contained in NP intersection co-NP. So having that, once we have shown that, actually, we have strong advice that this class cannot self-NP complete problems. Why? Because if you show that, no, let's talk about this later, maybe. Okay. Or maybe you can relate it to this second problem. No, okay. Yes. Questions? If you have questions, come to me. Form groups, work together. All right. Exam is over. So how did it go? So I was walking around. I think many people tried that and did pretty good on this. It's nice to see. So just some maybe concluding remarks on this lecture. So what we did is we looked at complexity theory and then tried to say something about the notion of causality. What happens to a computer if we allow for closed time-like curves? This was kind of the the final thing we arrived to. And we did this based on this NP hardness assumption, which gives us a tool to test theories, whether they could be in principle realized or not. And so this is, I really like this because we can kind of jump between computer science and physics back and forth and learn something about the other field from looking at from one field. So if you look from computer science to physics, we can learn something about physics from looking from computer science and vice versa. So this interdisciplinary flavor is what I'm interested in most and what I like most about this work. Still, there's a lot of work to do. So we have seen that the Deutsch model, well, I told you that the Deutsch model can solve NP complete problems efficiently. So as well, the the P closed time-like curves model, which kind of would tell us that these two models, if you accept the NP hardness assumption, are not realizable. But it still leaves open the question for other models to be discussed. Yes, having said that, I hope you enjoyed this lecture and this problem set. And if you have questions or remarks, or if you want to have the solutions or the questions, the problems or notes or whatever, you can just write me an email. Oh, sorry.
I'll ask you to provide a
Yes.
comment.
Oh, sorry. Yes.
Okay, Conrad.
Good. But you can also just write me an email if you have, like I said, comments, suggestions, if you want to know the solutions or whatever, references. Yes, and with this, I'm really happy how you participated. It was a pleasure. Thanks for taking part to this course. Thank you. And also thanks to Gibran and his team for this great organization and making this possible. Thanks.